motion of a charge in uniform magnetic field or any magnetic field. We know that whenever a charge is in motion in a magnetic field, it experiences a force given by F is equal to Q V cross B. Thus, the force on the charge is at right angle to the plane containing velocity and magnetic field. Again, we know that if there is a force at right angle to motion, then such force provides the necessary centripetal force and the particle undergoes a circular motion. Let us discuss about motion of a charge Q in magnetic field B. Moving with a velocity v. Let B be along positive x-axis and V along positive y-axis. Then force on the charge, force on the moving charge in magnetic field B is F is equal to Q V cross B, or here you can write V Q V I cap, sorry, V J cap cross B I cap. Or F force due to magnetic field, or FB is equal to V cross B, J cross I is minus K. This is minus Q VB B K cap. Thus force is along negative Z axis. Velocity is along positive y-axis. Hence, the particle will undergo circular motion in YZ plane. Since force is along negative Z-axis and at right angle to velocity, so this force will provide the necessary centripetal force. Fc is equal to m v square by r, where r the radius of circular path and path of motion is in YZ plane. because we have no in circular motion. Suppose r is the radius, v is the velocity, then centripetal force is directed towards center. If r is the radius, therefore this particle will undergo circular motion in yz plane. Now the magnitude or Fc is obtained from the magnitude of the force in magnetic field, or m v square by r is equal to q v b. Or r is equal to mv by qb. So here we find one thing, that if velocity is more, momentum is more, and charge is a constant, magnetic field is a constant. Therefore, more the momentum, more is the radius of orbit. More the momentum, or kinetic energy of the particle, more is the radius of circular path. Again, here you can find out v by r is equal to qb by m, and this v by r is angular velocity omega. Omega is equal to qb by m. Again, omega is equal to 2 pi by time period of one complete revolution, that is qb by m. So here t is equal to 2 pi m by qb. Another thing we find here, that the time period of revolution is independent of velocity. So if velocity more, radius is more, but time period is independent of velocity of the moving charge. It is observed that time period of revolution is independent of velocity of the charge of the charged particle. But if the velocity is at an angle with magnetic field, suppose theta is the angle between velocity particle and magnetic field, then we can say that here there are two components of velocity, Vx along direction of magnetic field and another Vy at right angle to this magnetic field. Then what is the nature of the motion of the charge? So we can find that due to the velocity Vy in magnetic field B, the force is again along negative z axis. So due to Vy, the particle will move in a circular path in YZ plane. Now, since there is another velocity along x-axis, so simultaneously the particle will undergo in the form of helical motion. If theta is the angle between V and B, then V is equal to Vx I cap plus Vy j cap, or this is V cos theta I cap plus V sin theta j cap. Due to Vy, the force is again along negative z axis. That is Fb is equal to Q V y j cap cross B I cap. This is j cross I is minus k, that is minus Q V y B k cap. Here Fc is equal to again Fb, or you can say that m Vy square by R is equal to Q Vy B. Or Vy by R is equal to Qb by m. This is omega, or 2 pi by T is equal to Qp by m, or T is equal to 2 pi m by Qb. This is the time period of completion of one circular path. Thus the particle will take a helical path, and P is the distance travelled by. Due to Vx, the particle will drift along x-axis. Besides circular motion in YZ plane, thus the particle takes a helical path. Thus the particle describes a helical path pitch is the distance travelled in one circular path, or pitch is equal to Vx into T, that is V cos theta into 2 pi m by Qb. Radius of circular path is the radius of helix Now let us discuss about motion of a charge under electric field and magnetic field when applied to a charge simultaneously. Suppose electric field is along y-axis and magnetic field is along z-axis. Electric field along positive y-axis and magnetic field is along positive z-axis. Now due to electric field, the force will be along the field. So this is the force under electric field. And due to magnetic field, the force will be at right angle to the plane. Suppose v is the velocity this way. So v cross b will be ij, that will be opposite. So if the two forces are in opposite direction, then the particle will move along the net force. But if the two forces are same in magnitude, then particle will move undeviated. Consider a charged particle Q moving along x-axis with velocity v. It is subjected to E electric field along positive y-axis and magnetic field along positive z-axis. Or we can say that the two fields are at a right angle to each other. Magnetic field along z-axis and electric field along y-axis. The two fields are at right angle to each other. Now, resultant force on the charge Fe, according to Lorentz force, F is equal to Fe plus Fb. So this is Fe is equal to Q E J cap plus, due to magnetic field, the force is Q V I cap cross B K cap. So here you can find Q E j cap. This is I cross k is minus j. So it will be minus QVB j cap. It is observed that the forces due to the two fields are antiparallel. And if net force is 0, if F is 0, then the particle moves undeviated. The particle moves undeviated. Or you can say that EJ cap minus QVB, J cap is 0, or E is equal to in magnitude QVB. Oh, here. Oh, it is like this. We have taken Q as common. So Q is equal to EJ minus VBJ, or it is like EJ cap minus VBJ cap is 0, or E is equal to VB, or V is equal to E by B. This V is known as velocity selector. That is, for certain value of E and B, the particle moving with velocity V will leave undeviated. With this principle, Thomson measured the specific charge of an electron. Specific charge, that is E by m, of an electron. And this principle is applied in mass spectrograph in order to discriminate a particle of certain velocity. In mass spectrograph, this principle is applied to discriminate or isolate an ion or charge of certain velocity just by changing the value of E. Suppose there are a number of particles moving at different velocities, because it depends upon the mass and effect of the fields. Hence, a particular ion can be studied or separated from a mixture or combination of different particles.